if you have a uniform magnetic field in a region of space and a surface, so that the field goes through the surface, we say the flux of magnetic field going through that surface is denoted by phi b, and we say it is the magnetic field intensity times the area if the area is perpendicular, but if the area is not perpendicular, we define area vector, and we say b times area times the cosine of the angle between the area vector and the b field. In this point, b is this way, area vector is this way, the angle between them is phi. We say dA cosine phi. Unit of magnetic flux is what? Unit of B times unit of area, right? What would that be? Tesla meter squared. Tesla meter squared. We have a name for this. For the electric flux, we don't have a name. But for this one, we have a name. It's called Weber. And it is denoted by WB. So 1 Weber means 1 Tesla times meter squared. And again, if the magnetic field is not uniform, then you do integrate over the surface. So if you have a non-uniform B field, also non-flat surface, you get phi b is equal to integral of a small piece of this, b dot dA. This, by the way, can be written as b dot a, right? This is magnetic flux. And the Faraday's law says that the EMF, electromotive force, created in a loop is equal to change of flux. Faraday's law. EMF is equal to rate of change of flux. Usually they write Faraday's law as this, as integral of E dot dL equal to negative d phi b over dt. Usually you see this one for Faraday's law instead of you separated. And this negative sign is because of Lenz law. All right. So now if you change the flux through the coil, it creates an electric field inside the coil, and that electric field creates the current that you observe here. Right? And this flux that changes can change in many different ways. You can have magnets moving around and changing flux. You can have nothing moving, but the magnetic field changing inside the coil that changes the flux, or you change the coil. All right, so this is basically Faraday's law. And then Lenz law says that the current that is created in the coil is in a direction whose magnetic field opposes the change in the original flux. Lenz law. For example, let's say you have a coil here. This side is closer to us. This side is far away. And there's a magnetic field here, B. Let's say B field is uniform, but it increases with time, right? So flux is going into the coil and increases in that direction with time. So let's say B is this way and increasing. Right now there is no current in it, but when the B increases there will be current. Which direction is that current? Lenz law says that the induced current in a loop is in such a direction as to oppose the change of original flux. What does that mean? So this flux is going into the loop downward, right? And it is increasing, so the change is downward. When a vector increases, the change is in the same direction as the vector itself. For example, if B is like this and it's increasing, means later on B is like that, right? This is B1, this is B2. And then if you calculate B2 minus B1, what do you get? B2 minus B1, you get this. This is B2 minus B1. You get this is delta B, right? So this is delta B and B are in the same direction. Now, Lenz law says that the induced current creates its own magnetic field that opposes the change in the original flux. So if the flux is downward and it's increasing, means the change is downward into the loop. So the induced current is a magnetic flux that is opposing that. Means that the magnetic field of the induced current will be opposing this delta V. So it will be up. And then the current has to be from right-hand rule. The current has to be like this, looking from up. It will be counterclockwise. So it is like that. But if it's decreasing, if B is decreasing, then B1 is bigger than B2, right? This is B1, this is B2. It goes from B1 to B2, decreases. It's downward, but decreases. So what is delta B? Delta B is B2 minus B1, right? Final minus initial. So that's B2 minus B1. This is B2 minus B1. Well, what is sum of these two vectors? A vector from here to here, right? This is delta B, right? So it means that if the B field is downward and is decreasing, the change is upward. And then the induced current creates its own magnetic field that opposes this one. Therefore, it makes a magnetic field downward. And therefore, it should be in the other direction. And that's why when you do this experiment, you move the magnet one way. You see here, with the magnet here, you move one way, you get current in one direction. You move the other way, you get current in the other direction. See? This way goes that way, it goes the other way, right? Or if you flip the magnet, you go this, go that way, go back the other way. So that's Lenz law. So in order to see which direction the current is, we have to use that. And there's a shortcut to that. You can say that if the flux in any direction is increasing, the magnetic field of the induced current opposes it, opposes the original. If it is decreasing, supports it. That doesn't want the flux to change. The induced current doesn't want the flux to change. So if the flux increases, it opposes it. If it's decreasing, it supports it to not make a change. All right, so this is Lenz law.